Okay, we're back and welcome to Lecture 1 on Propositional Logic. Now, this lecture series will be split into what one may call two parts. The first part being development of propositional logic, whilst the second part will focus on using our propositional logic in proofs. So it's a more of a theoretical development first and then more application towards proofs. So let's start with propositional logic. Here we start with truth values, true or false, denoted by T or F, and statement, proposition, that is an expression which has a truth value of true or false, and not both. So that's good. Propositions are the things we're hoping to prove, and they may either be true or false, defined by their truth value. Examples include statements like the earth is flat, which is a statement which has truth value false. Another one, x squared equals 2. X squared equals 2 is not a statement, because remember, as we said, a statement either has truth value true or false. X squared equals 2 can have statement value true or false depending on what you choose x to be, but here an x is not specified, so this statement x squared equals 2 is neither true nor false, so it doesn't count as in our sense, a statement or a proposition. And another example is there's a rational number x for which x squared equals 2. So this one has truth value false because there isn't a rational number for which x squared equals 2, and compared to the previous one, it actually has a truth value of false, and it doesn't depend on anything because we did specify that a rational number which effectively, since there is no such rational number, knocks out all rational numbers and leaves us with a truth value of false. And a final example, there's a real number x for which x squared is 2, which has a truth value of true because indeed there is a real number x for which x squared is 2, namely the square root of 2, which is real and not rational. So, statement variables. Statement variables denote unknown statements. So for our purposes, we'll use the letters P, Q, and R as our statement variables. So in essence, statement variables stand for statements which we know have truth value true or false, but we do not know the exact statements. One analogy is the use of the letters X, Y, and Z to stand for usually real numbers, so although unknown, for unknown real numbers. Logical connectives. Logical connectives connect statement variables. Logical connectives are applied to statement variables to form statement forms. So examples of those are not P, where P is our statement variable, and the not symbol, the sign symbol, is our connectives. And here we have two other connectives, but we'll get to know these connectives in the next few slides. So we'll move on to knowing these connectives. The first of these connectives is the negation connective, meaning not, written with not P. Now not P is true, or has truth value true, truth value T, if and only if P, the statement variable, has truth value false. So here's the defining table where the statement variable P can either have truth value true or false, and not P essentially has the opposite truth value. An example would be if P stood for James wears a red shirt, then not P would stand for James does not wear a red shirt. Our next logical connective is the conjunction, or meaning and. So this operates on two statement variables, P and Q, written P and Q, or with the wedge symbol. Now P and Q is true if and only if P is true and Q is true. That is, P and Q are both true at the same time. Now for this, our defining table is given on the right, where P and Q statement variables can have truth values of true or false, and this gives rise to what is this? 4 combinations. That is P true, Q true, P true, Q false, P false, Q true, P false, Q false, and P and Q only true when both are true, and that's only in the first line where we have true true, and in the next line P and Q fails to be true, that is, it's false because now Q is false, and it's false in the next line because P is false even though Q is true, and in the final line it's false because P and Q are both false. An example of the conjunction operator or conjunction connective would be if P stood for the statement x is greater than 1 and Q stood for x is less than 10, then P and Q would mean that x is greater than 1 and x is less than 10. Okay. Disjunction, meaning or. P or Q is true if and only if either P is true or Q is true, or both. Now the disjunction operator or the or operator is different from our natural use of the word or. Often when somebody says something like, would you like an apple or a pear, they mean would you like either an apple or a pear, and not both. But our or includes the option of getting both. So having a look at the defining table, we see that P or Q is true when P and Q are both true. So yeah, and true when only P itself is true and Q is false, because it is or, not and when and when P is false and Q is true, P or Q is true, and when they're both false, and only when they're both false, P or Q is false. An example of this would be if P stood for the glass is full and Q stood for the glass is empty, P or Q would stand for the statement the glass is full or the glass is empty. A note on statement forms. Statement forms are not the same as statements. Statement forms represent arbitrary statements. That is, statement forms focus on the structure. An example of this difference is the following. We have statement 1 saying x is greater than minus 11 and x is less than 20. Statement 2 saying the dog is brown and the cat is ginger. Both are statements, one about a mathematical object, x, and the other about the colors of dogs and cats. Statement 1 and statement 2 are different statements. However, they are of the same form, the form statement P and statement variable P and statement variable Q. To get a feel of this new language, let us give a comparison with the natural language. Let x be a real fixed number, and let us denote by P the statement x is greater than 0, by Q the statement x is less than 2, by R x is equal to 1, and by S x is equal to 2. In the natural language, we would write a statement such as 0 is less than x is less than or equal to 2. This translates symbolically to the statement form P and Q or S. In the natural language, we would also write something like x is greater than 0 and x is not 1. Symbolically, this would translate to P and not R. Truth tables. Truth tables are used to determine the truth value of a statement form given any assignment of truth values to the involved statement variables. As an example, we'll look at the exclusive OR. That is the statement form P or Q and not P and Q, involving the statement variables P and Q. Filling in the table, starting with the truth values true for P and Q and true for Q, we have that P or Q is true and P and Q is true. Since P and Q is true, not P and Q is false. Now, as P or Q is true and not P and Q is false, their conjunction is false. Similarly, we can fill the rest of the table with the given truth values of P true, Q false, P false, Q true, and P and Q both false. Tautologies and contradictions. A tautology is a statement form which has truth value true for every assignment of truth values to the involved statement variables. A tautological statement is a statement whose statement form is a tautology. A contradiction is a statement form which has truth value false for every assignment of truth values to the involved statement variables. As an example, we have that P and Q and not P or R is a contradiction, as if we work out its truth table, we find out that its final truth value is false for any assignment of truth values to the statement variables P, Q, or R. In addition, we have an example of a tautology in the statement form not P and not P or Q.